All right, everybody, this is worksheet 4. We're talking about resistance, Ohm's law, Kirchhoff's rules, and then resistors in circuits, and then a little bit of power at the end there. So this is kind of a longer one, so I'm going to do my best to keep us on pace here. But so first we have this equation of electric current. We should remember this, the change in charge over time. This was from last week, but it comes back up this week. And then we have the resistance of a wire, where that this symbol here is the resistivity, we have the length, and then we have the cross-sectional area right there, right? So resistance itself is, the electrical resistance of a circuit component or device is defined as the ratio of voltage applied to the electric current that flows through it. So that's effectively, the resistance, R, it's more related to Ohm's law, is equal to the voltage divided by the current that goes through it. And if we just rearrange this equation, we'll see that we end up coming to Ohm's law there. Okay. So let me move my notes here. Next thing we're looking at is Kirchhoff's rule. We just have to remember that that is composed of two things, that being the junction and the loop rule, right? So a junction is any point where the current can kind of split and go two different ways. So like I imagine it like something like this, right? And we have like a resistor here, a resistor here. This point right here would be considered a junction, right? And that's conversely to like this, where we have like a resistor, another resistor, like right here. It's like obviously no junction. This is not a junction. All right, so I can delete that. And then something about Kirchhoff's that's kind of important is that whichever way you define the current will kind of dictate the sign you put in front of the IR, right? So let's say we have like this system right here, a little resistor right here, and we don't know which way the current's going, but we just make it up and we call this I1. There's like normally like a multi loop situation, but let's just call this I1. Okay, and then if we have our loop going like that, actually I think it'll be better if I show you this in an example. I'll come back to that. Okay, so sorry about that. Yeah, I was like, this drawing's not going to be very clear. So if we have a current, if we have resistors, current is the same in series, and then we have their voltage is the same in parallel, right? So it's like opposite of what we saw with capacitors. And then resistors in series here, we just add them up, again, different than opposite of capacitors. And in parallel, we do that inverse addition. And lastly, we have this this electrical power equation here, and we see that we have all these different ways of solving, and it kind of just depends on what you're provided, okay? So, I don't really have anything else to write about here, but I think we should just dive into these questions. So here we have the ratio of resistance of a 10 meters of aluminum wire that is 2.2 millimeters in diameter. And then we want to see that ratio compared to a 24 meter copper wire that is 1.8 millimeters in diameter. We're given the resistivity values of each of them. So that means we can solve for the resistance, the ratio of resistances by first, dealing with aluminum. So let's say that the resistance of aluminum is equal to that resistivity value, the length over the area. And the same thing with copper here, right? We can solve for this guy like this. All right. So this is of copper and length over area. So we plug everything in here. We'll get 1.68 times 10 to the minus 8. And the units of this are ohms times meters times 24 meters. And then divided by the area, which is going to be 1.8 times 10 times 3 divided by 2. We'll square root that and pi it, right? So we're going with like a wire, so we have like a diameter. So we're going to look for the area of the circle there. And that equals to 0.158. We do the same thing here, 2.65 times 10 to the minus 8 times the 10 meters. That's the length, area of the circle. So that's pi r squared. We're just dividing the diameter by 2, right? That equals 0.0697 ohms. Okay, and we can find the ratio of resistances by putting, RAL over RCU, which is equal to 0.0697 over 0.158, that equals 0.44. Okay, and then with ratios, the units cancel out, so that's what we're just done right there. Okay, so that one's pretty straightforward. Just plugging everything in. And this next one, we're dealing with a student hangs onto a DC current transmission line carrying those amount of that current with both hands. The line has a resistance of 2.5 times 10 to the minus 5 per meter. So, that should be superscript. Sorry about that. Per meter, and the student's hands are 1.5 meters apart. What is the potential difference between her hands? So we're given a few different things here, starting with the current. So we know the current is equal to 4,100 amp. We know the resistance is 2.5 times 10 to the minus 5. And they say ohms per meter. And we know the distance of the hands are 1.5 meters apart. Okay, so when we do V equals IR, the important thing here is, we plug in current. And this is kind of showing you application of Ohm's law here. We do 2.5 times 10 to the minus 5. Since we know the resistance per meter, we can find it, just like generally by canceling out that meter variable by multiplying by 1.5 meters right here. You'll see that these 2 meters units cancel out there, and then you just plug everything in, you come out with 0.154 volts. Okay. All right. So those are kind of like, the introduction type questions, and then now to get into the meat and potatoes of this whole thing here. So now we're looking at a Kirchhoff's law question, and I know that because I see like the three, I can imagine like there's 3 different things. It's this guy, and the whole thing, right? So I know I need to break it down using the junction and the loop rules. So I can just, identify my junctions. I'd like to do that first. So I always use blue, I call it A, and I call it B, right? So I have my 2 junctions identified here. And then I'm going to assign my currents. I can just really pick whichever way I want to, but normally I imagine like, this is like the minus terminal, and this is the plus terminal. So it's probably likely that this current is going this way. I'm going to call this I3. And this again, minus is the plus terminal. So it's probably likely this is going this way, and I'll call that I2. And, minus and plus. So it's probably likely that this guy, the current in this upper portion here, call it I1, is going upward. Okay. So now I've identified my 3 currents here. I know where my junctions are. And I can say my junction rule is then equal to what goes in is equal to what goes out. So what's going into this A position, we have I3 going in. We have I2 going in. So we have I3 plus I2 is equal to what goes out. What goes out here is I1 is equal to I1. We've created our junction rule. And I like to simplify. I like right off, or it's up to you, but I just like to do the simplification right off the bat, because I know I'm going to need to rearrange it and plug it in as needed. So I'll call that part 1. And then part 2, the loop here, I can just choose my loops. I normally like to just do the 2 interior loops because they're typically easier. I'll actually start up here. And then they have like typically less things included than the full loop on the outside. So I'm starting here. I have a loop going clockwise, and it agrees with the direction of current 1. And nicely, it also agrees with the direction of current 2, right? So our arrow is pointing, our current arrow here is pointing like this with respect to I1. With respect to I2, it's pointing like this. The loop we defined right here is like this. So, it's in accordance with everything else here. So we define our loop. We're going to say, loop equation number 1, definition of that is that it equals to 0, each component like in sum. So I like to start at the biggest battery. So since our current is pointing this way, and what we define as our loop is pointing in the same way, so they agree in the direction they're pointing, we start with a positive 18, right? Positive 18 volts. We continue moving along to this position. Again, our current is pointing this way. Our arrow is pointing this way. And because they're pointing in the same direction, we do minus 3. What's the current there? I2. We continue along. We have this way. We go up. We go this way. We now hit this resistor. We see that the current is pointing in the same direction as what we defined as our loop here. So again, minus 2. What's the current here? I1. Okay. And we continue moving along. We hit this battery. Our battery, the current going through this battery here, I1, is in the same direction as what we defined as our loop. So plus 2. We're going to clean this up. We're going to get 0 is equal to 20 minus 3 I2 minus 2 I2. All right. We need to do another loop, right? Because we need 3 equations for 3 unknowns. And I like to, like I said, I like to use those interior loops. So I'll just do this one in, I don't know, green, whatever color this is, green. Call that loop number 2 here. I like to start behind my biggest battery, so that's at 20 position. Again, our current is going the same direction as our loop through this battery. So we can say 0, or let me draw the, say 0. Our loop and current go in the same direction. So 20. We continue along the position we hit here. Again, our current is pointing this way. Our loop's pointing in the same direction. We say -5, and then we say I3. The reason why we're able to do this actually is because, you think about it, this is like the voltage, right? And the sum of the voltages in respect to a loop equals 0. What does Ri equals? V equals like IR, right? So V. So that's why we're able to, I guess I'm like writing a weird order, right? But this is the resistance here, and this is the current. So effectively, I'm writing the voltage of each one is equal to 0. So that's kind of like what's going on there. Anyway, kind of a tangent. We continue moving along. We go this way. Eventually, we hit this resistor, this 3 ohm resistor. Here, the direction of the loop kind of clashes with the direction of the current, which is going this way. So that means it's going to be plus 3 I. What's the current here? 2. Okay. We continue moving along. And now plus terminal first, so current is going this way through the battery, this way with respect to that top area. We hit the plus terminal first, that's minus 18. So we're going to clean up this equation. We'll see that we get 0 is equal to 2 minus 5I3 plus 3I2. Okay. So at this point, we're going to have, 3 equations with equation like 1 over here, 2 over here, and 3 over here. We're going to be able to combine the 3 equations, 3 equations. You can like rearrange them and plug them in. I went over that on the homework review. So if you want to look at how to solve a system of equations, look at that. But just to save time and going through the algebra, I'll just tell you that I1 is equal to 166.31. I2 is equal to 96 over 31. These are all units of amps too. And I3 is equal to 70 over 31. Okay, so that's the current through each of the resistors shown here. The only other thing I want to know, and something that I said during the recording, I guess is kind of your preference though, but if in fact, I'm going to use this blue to show, or I'll use orange actually, orange to show what's wrong. So if in fact I define the current going through this 20 position right here as going this way, what I got for I3 is minus 70 over 31. But since the current does in fact go this way, I got a plus here, right? So there was no negative. And because of that, I can leave it like this. But if you get the negative, professor said that you don't need to write the correction, basically saying, guess wrong, should be positive. And you just leave it as the negative because he knows it's relative to the question. So in that recording, I say you should correct it and say that your direction guess is wrong and the current does in fact go, like you would say in the case of I3, you would say it goes counterclockwise. But since he said that's fine, you don't have to worry about that. And that's only the case if you end up getting a negative here, right? So that tells you that the current is this way is wrong. And again, the little trick I use to be like, which way the current most likely goes is I look at the minus terminal, I look at the plus terminal, and then I draw the current that way. So I look at the minus and look at the plus, I draw the current that way. The minus and look at the plus, I draw the current that way. That's kind of a little trick that's more often than not correct. All right, so now everyone's favorite, we have this circuit. Oh, actually, I'll pause the recording and take questions because I've just done a few questions in a row. Someone just got a good catch here that this should be an I1 right here. I accidentally wrote I2, but I'm sure everybody else caught that, seemingly except for me. So yeah, oh, I'm sorry, right here, I1. All right, let's move it on. So here we have this resistance, a circuit full of resistors, and we want to clean it up. And we want to determine the voltage across the 6 ohm resistor and the current through that 6 ohm resistor. So let's first see where that, so that's going to be this guy. So lucky for us, that guy is super embedded in the system. So it's going to require we really clean up this and work all the way through it. So typically what you want to do is start like the furthest away you can. So like that's in this area. And then here we can see like, we're going to want to start by looking at these guys in parallel. Technically, I guess you could do these ones first, but I see this triple whammy right here, and it's calling to me. So I like to write a box around everybody in parallel. With resistors in parallel, what do? We do that inverse addition. So I'm going to say 1 over the resistor in resistors in parallel is equal to 1 over 3 plus 1 over 4 plus 1 over 4. You're going to clean this up. I'm going to call it RP, and that's going to come out to be 1.2 ohms. Okay. So at this point, you're going to redraw the diagram. So that's always fun. Like this. Okay. That's right. Let's see here. All right, and so now we have, like I said when I did the capacitor thing, I like to put it in quotes here because, you know, there truly isn't a 1.2 resistance resistor at that position, but you know, it's effectively there as we kind of clean up the system and condense it as we solve. Okay, so the next thing that is calling to me is another one in parallel. That's this guy. I want to get this guy in parallel because then I can see I can do a bunch of combinations in series. So again, parallel, we solve the same way. And that's, you know, this right here is equal to this right here. So again, we clean it up. We're going to say 1 over RP is equal to 1 over 10 plus 1 over 6. All right. And then RP is equal to 3.75 ohms. So again, we get to redraw it. All right, what we're left with is this. All right. So here, you know, we have the 1.2, and now here we have another, like effectively the 3.75. I do it in quotes. It helps me remember. And then the next thing we can do, you know, is we see these two guys in series, and actually, if you really want to be a physics whiz, you can do this lower one that's also in series at the same time, right? So we can call this, you know, series 1, and we can call this series 2. So when I clean this up, I'm going to say RS2, and that's going to be equal to the sum of, you know, I think this one was, let's see. So 5 and 7, 5, 7 ohms, and this last guy over there was 1 ohm. We can just do this double whammy action. 5 plus 7 plus 3.75. And for RS1, it's 1.2 plus 1. So that equals 2.2. And that equals, what's that? 13, 16, 75. Wait, 15.75. Did I do that right? No, wait. My key is wrong. All right, so 15.75, that was right. Okay, so now we clean this up even more. So now what we have is, you know, the batteries here goes this way, resistor, resistor, resistor. All right, over here we have that 2.2. And down here we have that 15.75. Again, we have these two in parallel. So parallel. What do we do with two resistors in parallel? We do that inverse addition. So I'll say 1 over RP is equal to 1 over 2.2 plus 1 over 15.75. And RP comes out to be equal to 1.93 ohms. Okay. So we then redraw again. We have our battery right here, this one. Now we just have this one and back. And this is our 1.93 ohms. Looking at this last one, we have these two in series. This guy's, it's 2 there. what do we do with resistance series? We just add. So now we have that, equivalent resistance here. So 2 plus 1.93, 3.93. Okay. Wow. So we determined, the equivalent resistance of the circuit. So that's part one. Let's call that Req is equal to 3.93 ohms. All right, nice. So now we want to find the voltage across the 6 ohm resistor and the current through the 6 ohm resistor. So let's first look back at our little key here, right? So current is the same for resistors. Current is the same when there's resistors in series, and and voltage is the same for resistors that are in parallel, right? So let's just be really clear about that. Let's write that. Oh, where are we? So I'm going to say resistors in series have the same current, okay, and then resistors in parallel have the same voltage. Okay, so that's confusing. I and then V here. All right. So now we can start working kind of this out backwards. So looking at E, we have, let's call this E actually. I was like, why did I call it E? And I realized that I labeled it on my key, and that's actually a good idea. I should do this from now on because it helps people follow. And this original one. Wait, am I missing one? Oh yeah, because I did 2 at the same time. All right, so A. So the first thing is, looking at E, we have 2 resistors in series. So what's the current through them? They have the same current. So let's find that current value. So remember, V equals IR, where V, the total voltage of the system. Oh, we don't have that yet, do we? Oh, it's given. Is 12 volts. Yeah, it's like the voltage drop throughout the whole thing. So we want to find the current, so we can rearrange this to V over R is equal to I. We can say 12 over 3.93, and that's equal to 3.05. So therefore, the current through that 1.93 resistor and that 2 ohm resistor is both equal to 3.05, right? And because they're in series, they have the same current. So then if we want to find the voltage now through these ones right here, we're going to need to use that current value and just and work backwards, right? So I'm going to say the voltage through the 1.93 ohm resistor is equal to the current there we just found as 3.05, and then times the resistance, which we solved for previously, as 1.93. So that 1.93 is equal to 5.89. Okay, and this resistor right here is made up of 2 resistors in parallel, and the voltage is constant for 2 resistors in parallel. So therefore, we can now apply this voltage to this one to find the current at this position, because we know the current at this position is constant in those above. So we can set I is equal to V over R, where that's equal to 5.89. We just found that, divided by 15.75. So that 15.75 is this position. What does that come to be? Let's see, 0.374 amps. Okay, so we found the current through that 15.74. And we can now use that understanding to establish what the current is through all of these ones, because recall, resistors in series all have the same current. So now we can expand this one even greater to find the current through that R6 position. So to do that, we'll say the current through the sixth position is equal to the voltage, that's 1.4, wait, one sec. No, I'm not ready to do that yet. Okay. So the next thing is we want to find the voltage through this position, because resistors in parallel have the same voltage. And with that, we'll be able to find the current here. So we'll say V, continue up here, V 3.75, that's this position, is equal to, one sec. Oh, I'll answer that question in a second. V 3.75 is equal to the current there times the resistance, right? So the current there we just found is 0.374. And then the resistance here is 3.75. So that comes out to be 1.4. All right, sorry, I'm kind of running out of space here. And now we know the voltage here, and we remember that resistors in parallel have the same voltage, where this is the 6, right? So this is where we want. This is the 6 ohm. And we know that these two are in parallel. They have the same voltage, and this voltage makes up what's here. We can now solve that final portion here. So to find the current through 6, we just use that 1.4 and then divide it by its resistance, which is 6. And that I6 comes out to be equal to 0.234 amps. Okay. And then the voltage there, this is kind of a double whammy, right? It's kind of a trick question. The voltage there we just solved for, right? This is 1.4 because that makes up this one, and then the resistors in parallel have the same voltage. So we'll say 1.4 volts. All right, this is so messy, but I think I'll zoom out a little bit and kind of get an overview, and then we can use the key as kind of the clean version. All right, let me pause the recording and oh, actually, this is a good question. So someone asked like how we got 12, and at first I was looking for it up here, but they actually gave it to us right here. So this is like the total voltage drop from this terminal to this terminal. If you like go through everything, is 12. So the voltage of the whole system, which you're going to plug in over here to get that. This is like where you plug in the equivalent resistance. It is 12, right? And that's given right here. So I too was like, wait, where did that come from? And then I realized. All right, let me pause the recording and take questions. All right, we're just gonna not do number 5. It's kind of a old style question here, and I feel like it's not one that we would see. So we have a power station in question number 6, which delivers that 750 kilowatts at that voltage to a city 5 kilometers away through 2 copper wires. We're given the resistivity, and we're given their both of their radiuses. What percent power can be saved if they were using a step-up generator, right? So that's now instead of 12,000, we're at 50,000. Yeah. So just by definition, like every wire has resistance, and it's normally just like we just normally kind of don't consider it like how we don't consider air resistance, but every wire has resistance, and given like these conditions where we're dealing with so much power and so much voltage, we can actually consider it here. So the power that will be like going into the wire is actually kind of less than what comes out, and that's unless we use these step up voltage things. So when you have when you see voltage lines, there's like the super powerful ones that are kind of in between the power station and your house. They get stepped up and they get really strong, and they come back down before they come to your house, and that makes it so that we don't lose as much, right? So we're asked to find like the difference that can be saved to reason to step up. So we need to solve this in kind of 2 ways. The first thing we need to address is how much power is delivered through the wires, and the next is how much power is lost through the wires, right? And in that comparison of lost versus delivered, given those 2 scenarios, that being at 12,000 or 50,000, we can kind of come to an agreement here of how much we save. So, and we expect to save it, right? Because we're using, in the case of a step up, that's kind of just like by definition, that's how it works. So the first thing I'm going to do here is I'm going to call it P delivered, right? I'm just call it PD. So power is equal to IV. I know we're going to be using IVs because we're given the current. Wait, are we getting current? No, we need to solve for a current first, but we're given power and we're given voltage. So we do a little bit of a rearranging action. You can see that we can say I1 is equal to that P delivered divided by the voltage one. So what's the power delivered by the power station? You know, it's 750 times 10 to the 3 watts. And then what's the voltage in the power delivered of like the first situation? 12,000. You get 62.5. Okay. The next thing you want to look for is the power loss. So to do power loss, we need P, call it PL, is equal to that I12 squared, times R. And we don't know what that resistance is, but we do know how to find resistance, where R is equal to resistivity times that length divided by the area. So if we do the math for that, we can say it's 2 times, and that's because there's 2 wires, right? There's 2 copper wires, times that resistivity value, which is given as 1.68 times 10 to the minus 8, times that distance, 3,000 meters, or 5,000 meters, sorry. Okay, 5,000. And then we divide that by the area here. So we know it's 5 millimeters, 3, and then squared times 5. So now we have a value for R, which is equal to 2.14 ohms. We're going to now do P lost is equal to that 62.5 amps squared times that resistance value, which is 2.14 ohms. Okay. So P lost in the 12,000 volt scenario is 8,356 watts lost. And say 12,000 volt option. Okay, that's a lot, right? So that's why like the step up is gonna, given it's like going through a step up, you expect that in the other scenario it will be much less. And if you don't get that, that probably tells you you're solving incorrectly, right? Okay. So now we can do the same thing, but with the delivered situation. So we can say the power delivered, call that PD prime. So this is with the 50,000 volt option, is equal to I2 B2. Again, we don't know the current that's going through there, but we do know the power delivered. It's going to be the same amount of power. And we know the voltage difference will now be 50,000 instead of 12,000. So we can solve for I2 using that same logic by saying 750 times 10 to the third divided by that voltage, 50,000. And then that's going to be equal to 15 amps. That's the current there. And then we can do the same logic, find P loss prime, which is again that 50,000 volt scenario. And we can say I2 squared times R. And instead of calculating R again, like we did right here, we know that it's the same wires, right? Nothing about the resistivity, about the length, nor the area has changed. So we can plug in that same R we found, except just using that correction for the current. So 15 squared times 2.14. This comes out to be 481 watts lost. And I want to say in 50,000 volt option. So again, this kind of agrees with our, right? It passes our check that in the step-up transformer option or in the step-up voltage situation, we have less power loss. So to do like a percent loss, this is like, like general chemistry, right? So we can see that the percent is equal to, that initial one. So 8,356 minus 481, that's what it is in the new scenario, divided by that 8,356, and then times 100. And this will tell you the percentage we save when using the 50,000 volt option over the 12,000 volt option, right? So it's just like per separate equation. So the key thing to note here is you first need to find the current, and that's because the power that's actually delivered, and the voltage that it goes through. The next thing you need to find what's lost, and to do that you need to recognize resistivity. The equation of power that includes resistivity is P equals to I squared R. We don't know what R is, but we can find it using the information provided. Doing that, you find what P lost is. We know that in a situation when the voltage is not as high, the power lost will be greater than that when the voltage is higher. And that's what we prove here. And then you do this percent difference calculation, right? So it tells you like what percent power can be saved using this scenario versus this one. Okay, you just multiply by 100 because it's a percentage. All right, so like I said, I'm gonna skip number 5, and depending on the next homework, I'll be able to better have an RC circuit for us to go through. I'll still solve it and post it online, but I don't think it's a good one because it's kind of different than what we've been seeing. But anyway, yeah, that's it for this worksheet. Thanks.